Thank you very much. Okay, hello everybody. Thanks for having me here. So this is some joint works together with the Bonn group working on a Maya dictionary, and we are part of the computer science team trying to provide some methods to find Maya glyphs derived from 3D data. So this is a brief overview about the presentation. So what drives us usually are 3D scanned objects, often with some text embedded. So previous presentations have been also about cuneiform tablets, and Bartosz is presenting in the parallel session about Aegean ceilings. For this presentation, it's also a bit different than the regular computer science talks, that we can also apply some hermeneutics at the end from our findings from these networks we can compute from extracted Maya glyphs. So, well, as maybe most of you know, from Maya writing, this was very well destroyed when the Spanish arrived. So everything kind of on paper is gone. Because they burned a lot of things, and the remainders of the Maya writing are mostly chiseled into stone. So you have these nice stelae and walls with inscriptions. So this is one example, which has also been 3D scanned by our group together with the Bonn group. So this is also a 3D scanning campaign behind it to gather all the fine details of these very nicely carved writing systems. As with photographs and 3D rendering with true to color, the top one is also a 3D model. It's not very suitable for doing recognition of characters. So we transform it with our software framework. We're in Tübingen and a workshop about it into a curvature representation where concave and convex parts are color coded in bright colors or dark colors. So this really tells you this grayscale image where is something flat, where some details are going on. Our test data set, what the colleagues from Bonn have in totally acquired a 2-digit number of inscriptions worldwide. The ones for the presentation today are from Guatemala, which are also by intention a bit far away in time and also in place. And we changed a little bit the color coding, so this, please remember, there are like signs extracted from a darker one and a brighter one, because this is important for the hermeneutics part towards the end. So what we start is doing what you know from other document processing areas. If you're dealing with Hebrew or Chinese, you have these writing systems which nicely write in blocks, not like cuneiform tablet, there you can't do this trick. So we use our curvature images before from the 3D model and find the regular raster from the Maya writing itself to get the single glyphs out of these inscription parts. Of course, there are some other elements, like here is a person standing, which are also taken into account. This one we have to filter out. And also this is a bit more future work. Maya symbols also exist in person or animal shapes. So what we are doing currently are the more simpler glyphs, which are on the inscriptions, and this will also work on the even more simplified one, which you find painted on pottery. So about a brief introduction. So it's always hard not having the colleagues from Bonn here, but there is someone in the audience I've seen before. Maya glyphs, they are composed of several elements. So you have this squared block, and usually you have to the left-hand side or right-hand side, top or bottom. So on all 4 sides of this square you can attach another glyph, which is a condensed, shortened version of this bigger central element. So this is the second task is to find the subglyphs themselves. This is also one which is quite easy to detect for a computer scientist, because it's a number. So Maya numbering also used a 10-base system. 1 dot is a 1, a bar is a 5, so this is a 4. And if this, I'm not sure if this is a calendar sign, so you can see kind of what day of the month it is. So to give you a brief idea. For the subglyph segmentation, we go back to our curvature data, and of course, because it's very fine, it shows all the small details in this 3D model, because on previous work we also have detected like fingerprints on cuneiform tablets, so we're getting actually a bit too much detail, and we wanted to break it down into subglyphs. So we are labeling, finding connected components for these areas themselves by thresholding. Using a double threshold, because there are some pixels or points in the images which are unclear where to put them together. Therefore, we use a method which is called random walker segmentation, which has as input here, like in color text, pixels which are already known to be part of a subglyph. Then the black ones where you know these are in the carvings in between, so they are blacked out, marked out, and then there are maybe some pixels left which are undecided, and by finding away from a tagged pixel, avoiding the black ones, going over the gray ones, we also add these kind of missing pixels to the connected components. What then is also important is conflict resolution, not only for war zones, but also in computer science, because we have, of course, areas which are somehow connected visually by their shape within a glyph. So glyphs within glyphs are added to the bigger ones because we know of this arrangement that there is something always on the sides and the center itself. And we also choose we try to split overlapping areas to put them in the right context. Then the clustering starts by the subglyph extent. So each subglyph is an image, so this could also be called clustering subglyph extents. Because if it's a kind of a widescreen or a landscape or portrait type of glyph, this has some meaning for the processing itself, because it's more like a suffix or prefix or something like this. So instead of merging all together, we start clustering by kind of their bounding box into some classes using a k-means algorithm, to start then comparing the subglyphs themselves. There we use a method which is called histogram of oriented gradients. So in image processing, you have an edge, which would be the part between a very bright and very dark part of the image itself. And we can look at the orientation of the edges within this image and do this blockwise. And then we get like an orientation histogram, how the edges align within the image. And if there is something similar and it's a coarser representation, we can say one glyph is similar to the other one. There's also something important to remember here. This is done in smaller blocks in the image. So the resolution for the classification here degrades a bit, which we'll also see what effect it will have for the final outcome. The clustering for the subglyphs itself is also then done within these bounding box classes themselves, but with one threshold. So although we have a relatively low number on parameters for the classification process itself. But towards the end, of course, we have to do some normalizations to start connecting these glyphs. So connections are done to build like a network of similar glyphs. We're saying, okay, we sort out every glyph which is a standalone, because there we can't discuss anything later. But if we have some portrait subglyphs, some small squared ones, we can start connecting glyphs by the subglyphs themselves. And we only count connections one, because otherwise we get too much tension in the network afterwards. Talking about tension, what's built up there is some sort of a force field. So we introduce several forces. One would be the attraction along similarity. So if we have like at least one connection, we say, okay, these two glyphs, they are like forced together. Then we have a repulsion. If something gets too close, so glyphs also like to have their like privacy space, so that they push other glyphs away if they come a bit too nearby. Also important to inspect the graph finally, and to make like a one big cluster, there's a weak attraction to everything itself. So this compares a bit to like galaxies, so the stars stay somehow in a roundish shape at the end of the day. So this, of course, there is some random affected, because the initialization is random, and then if they could also do a video, then it wiggles together, forming this subglyph sharing network. And here is something important showing off. You see that most of the, we put an emphasis on the darker colored glyphs. You see there are only rare connections between the dark and the bright glyphs because they are from different places and also from different times themselves. But they connect very well by the numbers. So here you have a bar for a 5, here 2 bars, so this would be a 10. And you see that because the writing also changes over time and region, these symbols from a similar period, okay, yeah, stay together. When we go into detail discussing this with Christian from Bonn, of course, he said, well, computer science methods always have a certain percentage not working very well. So we have sorted this one out. So this is the kind of worst example, and the reason probably is because there are too much fine details going on for the histogram of gradient method. So this part we have to improve in the future, because if there is just small details, Hock doesn't get it. Then we had these type of wrong connections, which were tagged like close enough, because they kind of represent what was like known in the 80s or 90s for where glyphs have been wrongly put into the same clusters also by humans. So this is something where we can say, okay, the human expert in the past have done mistakes here, so why shouldn't be the computer system allowed as well? Then these one are also kind of these mixed up ones with broken parts, which also can be confused by the human expert. And this was a starting point to discuss how to arrange the Maya glyphs, because there's no like numbering or lettering system. So we can use these measures because something is similar, can be confused. So you can put it in the Maya dictionary online next to it. Others, nobody does this mistake again. Then we have coming to the good examples where for some reason our system only used like central parts of the element, and even if there are prominent ones, they have been skipped and kind of tagged not important for finding a similarity. We have to check into this one, and we even could show that if something has been here, have been 2/3 have been broken off. We had a very nice match of a damaged subglyph. But we are not sure if this is robust enough, because when our number of glyphs extend, we have like a 2/3 chance possibility to match something wrong. So Christian was very happy about him. I told him, be a bit cautious. It's a nice result, but don't put too much pressure on it, because we have enough glyphs where the connections are properly done. Also, if there are some variations in size, so if you look at this one where you have like these kind of circular structures, this also is heavily damaged. Here it looks like you have these dots twice, so all these things are done properly. So we have more than enough serious examples for themselves. So this already brings me to the end of the presentation. So what we showed here is kind of a 2 minutes. Okay, thanks. It's like this last slide. So.
Keep going, no problem.
Yeah. So we've done a bit using computer science methods, sat down together, doing some hermeneutics, discussing about what method has what kind of influence on your results. We have some idea how we can help future users of this online Maya dictionary to show them which signs are probably easy to confuse if you're not so deep into Maya script. And of course, we will kind of export this knowledge from this project to others, things where we've done like 10 years experience in document analysis of cuneiform script. So this will be interesting to do something for the other data we have. And what's Bartosz presenting in parallel, sorry, this is the German title of the project. It's also about contextualization of Aegean ceilings using like 3D forensics. There we have some extra aspects, also looking at tool marks, if they're using drills or knives or whatever to cut these stones. So this brings me to the end. Like last year, we also had this workshop about our 3D software where we computed these images in the beginning. So this has been online now for a year, and also we were quite asked quite often, because we're Linux persons, is there something for archaeology? Can you provide us a Windows? So this is a version, this is today like a premiere for a beta version. I wouldn't, we're not yet sure if everything works, but you can try it out. You find also some YouTube tutorials to get into profile line extraction, so this relates a bit to the previous talks. And in December, we will have also a German workshop on building research in medieval time, also with GIS and 3D things going on. So, thank you very much.